Now we will discuss about Turing Machine in Module 5 of Theory of Computation. Before discussing about Turing Machine, we can see what is Chomsky Hierarchy. Chomsky Hierarchy gives the classification of formal languages into 4 types. That is Type 3, Type 2, Type 1 and Type 0. Chomsky hierarchy represents the class of languages that are accepted by the different machines. The category of languages in Chomsky hierarchy is as shown here. Actually, this is a hierarchy. Therefore, every language of type 3 or regular grammar is also of type 2 or context-free languages and type 1 context-sensitive languages and type 0 or recursively enumerable languages. Similarly, every language of type 2 or context-free is also of type 1 and type 0, etc. We have already studied about finite state machine, push-down automata and linear bounded automata. We have also studied about the class of languages they accept. In finite state automata, we have studied about the class of languages accepted by them is known as regular languages. In push-down automata, the class of languages accepted by them is known as context-free languages. And in linear bounded automata, the class of languages accepted by them is known as context-sensitive languages. Now we are going to study about Turing Machine, and the class of languages accepted by them is known as recursively enumerable languages. We have also seen the drawbacks of finite state machine, and those can be overcome by another machine known as push-down automata, and also various drawbacks of push-down automata also we have studied. So now we will discuss about the more powerful machine known as Turing Machine. As an introduction, Turing Machine was invented in the year 1936 by the famous mathematician Alan Turing. Turing Machine is an accepting device which accepts the languages known as recursively enumerable languages generated by type 0 grammars. In 1935, Turing described an abstract computing machine consisting of a limitless memory and a scanner that moves back and forth through the memory, symbol by symbol, reading what it finds and writing further symbols. The actions of the scanner are dictated by a program of instructions that also is stored in the memory in the form of symbols. This was the stored program concept of Alan Turing. All modern computers are in essence a type of Turing machine known as universal Turing machine. Everything humanly computable can also be computed by the universal Turing machine. Turing machine is an abstract computing machine that encapsulates the fundamental logical principles of the digital computer. So, the Turing machine can simulate any computer algorithm. From this, a Turing thesis has evolved. The Church-Turing thesis states that a function is computable if it can be computed by a Turing machine. No computational procedure will be considered as an algorithm unless it can be represented as a Turing machine. So the power of any computational process is captured within the class of Turing machine. And any computation that can be performed by some mechanical means can be computed by a Turing machine. Now we could understand who is Alan Turing and the importance of Turing machine. Now we can see the data structure of Turing machine. The important data structure used in Turing machine is the infinite tape and a finite control along with a read-write head. The infinite length tape is divided into a number of cells, and each cell can hold one symbol at a time, and the tape is an infinite length tape. Second thing is the finite control. That is, at a particular instant of time, the finite control is in a Q state. The Q states are divided into start state, halt state, and intermediate states. Start state is the state from which the processing of the Turing machine starts. Normally it is represented as Q0, and halt state is represented by H, and halt state can be of two types, that is an accept halt or a reject halt. If a given string is accepted by a Turing machine, then it is known as accept halt. If it cannot be accepted by the Turing machine, then it will reach to a reject halt state. And the states in between this start state and halt state is known as intermediate states and is normally represented as Q1, Q2, etc. The third thing is the tape head. The tape head points to one of the tape cells and it communicates between finite control and tape. So tape head can move towards left, right, or it can remain stationary. That is, without moving to left or right, it can remain in stationary mode. Now we can see various operations on the input tape. Three important operations are read, write, and movement of the read-write head. So first one is read or scan the symbol on the square under the read-write head. Second one is edit or update or write the symbol by writing a new symbol or erasing it. Third one is the movement of the read-write head. It can be either towards left or right or remain stationary. Left or right by one square so that machine can read and edit the symbol on a neighboring square. Now we can see the mathematical definition of Turing machine. M is equal to Q sigma tau delta Q0 hash H, where Q is a set of states, sigma is a set of input symbols, and tau is a set of tape symbols including hash. Here, hash is a special symbol known as the blank symbol. That is, after the input string, we are representing the remaining cells by using this blank symbol. So we are including this hash or blank symbol in the set of tape symbols. Note that we are not including the blank symbol in the set of input symbols. We are including it in the set of tape symbols. Next is the delta, that is a transition function or the next move function. It is defined as q cross sigma to q cross tau cross left or right or no move. The meaning is that from a q state, on accepting an input symbol, it will go to next state, q state, and the tape symbol can be overwritten by another symbol, and the movement of read write head may be towards left or right or no move. Next, q0 is the start state from which the processing of the string starts, and hash is the blank symbol, that's a special symbol which is filled in the last portion of the input tape, that is after the input string it is filled with the blank symbol. And H is the halt state. So halt state can be either accept halt or reject halt. Now next is the representation of Turing machine. A Turing machine can be represented by three methods: instantaneous description, by transition table, or by transition diagram. Now instantaneous description is the description of the Turing machine at a particular instant of time. At any one time, the machine can perform three basic operations that we have seen already, that is read, write, or move the read write head towards left or right. We can understand the instantaneous description with the help of an example. Here, currently the symbol under the read write head is 1 and the current state is Q2. So the symbols on the left of 1 are X and 0. Symbols on the right of 1 are 1 and hash hash hash, etc. This instant of Turing machine can be written by using instantaneous description, that is id is equal to x0 q2 1 1 hash hash hash. It means that from the state q2, now it is processing the input symbol 1 and the left of 1 is x and 0 and right of this one is 1 and remaining blank symbols. Now after this instantaneous description or after this instant, during next instant, the Turing machine may be in some other configuration, and that configuration is represented as delta of q2 1 equal to q3 y left. It means that from the state q2, on accepting the input symbol 1, it will move to next state q3. This 1 is replaced with the tape symbol, new symbol y, and the read write head will move towards left. We can represent this transition function or the configuration like this, that is after this first instant, during second instant the Turing machine will be like this. That is, now the finite control is in the state Q3 and the previous one is replaced with Y, and the read-write head is moved to left. That is, now the symbol under read-write head is 0. In this way we can represent the instantaneous descriptions. Now we can see the representation of Turing machine by transition table. Here a Turing machine is given, that is an example is given. Here Q state is represented from Q1 to Q6 and sigma is 0, 1, xy, tau is 0, 1, xy with the blank symbol hash. Then start state Q0 is represented as Q1 and blank symbol is hash, and H with the whole state is the Q6. The remaining symbol is the delta, that is a transition function. For this example, the transition function is defined like this. Now we can represent this transition function into a transition table. That is, in transition table, in the case of Turing machine, we are representing the current state and along with the tape symbols. So we can take an example. Here the entry Q2YR corresponding to the row Q2 and column Y denotes the transition Q2YR, that is delta of Q2Y equal to Q2YR. So from the current state Q2 under the column Y, that is Q2Y is equal to, we can write Q2YR, right movement Q2YR. So in this cell, that is for Q2Y, we can write Q2Y right, because the transition function is already defined for Q2Y as Q2YR. So in this way we can represent the transition table entry. Third method is by using transition diagram. Here also we can take the same example. So the corresponding transition diagram looks like this. Here also we can take a small example, that is a part from Q1 to Q2. The transition Q1 to Q2 is represented as 0x right, because the transition function delta of Q1 0 equal to Q2 XR. That is the first transition delta of Q1 0 is equal to Q2 X right. So from the state Q1, on accepting this input symbol 0, it will go to next state Q2 and input symbol 0 is replaced with the new type symbol X and read-write head will move towards right. So we can represent from Q1 to Q2, input symbol is 0, next symbol, that is 0, will be replaced with the new type symbol X and the read-write head will move towards right. That is represented like this, that is in the transition from Q1 to Q2. Now we can see the language acceptability by Turing machine. A language L is said to be recursively enumerable if there exists a Turing machine that accepts it. Recursive means repeating the same set of rules for any number of times, and enumerable means a list of elements. The Turing machine also accepts the computable functions such as addition, multiplication, subtraction, etc. and many more functions can be computed by Turing machine. A string W is said to be accepted by a Turing machine if Turing machine holds in an accept state. That is, from the start state Q0, on processing the string W, after a sequence of moves, after a sequence of transitions, if it reaches to an accept halt state H, then that input string W is said to be accepted by the Turing machine. A string W is not accepted by a Turing machine if Turing machine holds in a non-accepting state or reject halt state, or it does not hold. So formally we can define the language of a Turing machine. L of M is equal to set Q0W after a sequence of moves. It will reach to a final halt state, that is alpha 1, H alpha 2 for some H element of F, and there is no further move. Hope you have understood the session. Thank you.